Okay, well, first of all, I wanted to welcome everybody to the last meeting of the StraboSpot Structural Geology Virtual Workshop. We're very happy to have everybody here today. We've made it through a week. We are going to change the order of how we're going to talk about things today. We're going to do all the same things. Just so you know, because we have Rick Almendinger with us now and he has a time constraint, we're going to hear about some of the digital tools he's developing and perhaps a little bit about how they interact with StraboSpot. We're going to have a data management session from Doug. We're then going to take our quick break. After that, we're going to come back for user examples that Randy will lead us, and this is of your work. And then we're going to hold the last 20 minutes out for Nick Roberts to talk about Strabo 2. And I suspect you'll want to stick around for that because there's a lot of nice new features that will come out of that. It's also a work in progress, so it'd be nice to get some people's opinions about how that's working. So Rick is showing us his screen now, so I'm just going to ask him to take it away.
All right. Well, thank you, Basil, and thank you, Doug, both of you for the introduction and for the invitation to show these tools. The tools I'm going to be talking about today are two mobile apps that I've developed, Stereonet Mobile and GMDE Mobile. And in the context of this course, probably the most important thing is that these are both StraboSpot clients. One of the brilliant things about the development of StraboSpot is that they provided many pathways into the database. And I expect that these apps are only just the beginning of many people who might develop specialized tools to upload and eventually download from the database for different purposes. But I did want to start today with a brief comment about the profound transition our science is currently undergoing from these beautiful precision analog instruments, Brunt and Compass and so on, to these digital instruments, which are taking over astonishingly rapidly. And in, as little as a few years from now, the students will wonder why we ever use these things, just as today, most of us wonder why we ever use planimeters and things like that. So the transition to digital is really playing out in three fundamental phases or steps. In the first phase, we used our mobile apps just as data recorders. In the second phase, now largely complete, we're using our digital devices and the sensors in them to actually collect new data. And I think the third phase of this, which we're just beginning to get into, is to begin to use real-time computation in the field where we can test the hypotheses while we're still in the field. So that's how I see it. Here are two predominant examples of data recorders and all of the things that they provide in the list on the left. They also have other analytical functions, and they can both use orientation of the device to collect data, but they're predominantly recording data that we collect in the field, allowing us to take satellite images in easily and so on. In the second phase, we use device sensors to collect data, and you can see Stereonet Mobile, which you'll hear a lot more about in a minute, on the left, and FieldMood Clino, another fine client for using phones to collect orientations. Most people aren't aware that these mobile devices have an amazing number of sensors in them, which enable us to use the device orientation in space to collect data. And our work suggests that you can get as much as an order of magnitude speed increase using mobile devices. And what this does is it allows us to employ data redundancy like we never have before in field geology to increase the signal to noise ratio, something that our geophysicist colleagues have enjoyed for any number of years now. But because these are digital devices, they also have enabled digital sampling rates. Stereonet Mobile, for example, while you hold it on an outcrop, it measures, makes a new measurement of the orientation of the device in the outcrop every 100 milliseconds. In other words, it's measuring the strike and dip of a plane 10 times per second. And so the numbers that you see here recorded are the average and the standard deviation of those multiple tens of measurements that the device is making, all in the space of a few seconds. And this helps smooth out transients in electronic signals and things like that. Another trend that we're going to see a lot more of is augmented reality. So augmented reality is basically where you use the device camera and you overlay information on it, which is important to users. And in Stereonet Mobile's case, it uses the device camera to make sighting measurements along bedding planes or along other planes of interest, rather than putting the device actually on the outcrop. Of course, you can do this with a Brunton, and it's always a challenge to teach students how to do this in the field, because they have to balance a lot of different things. But with Stereonet Mobile, you use the camera, and the overlay shows you, for example, this green dot says that you're within a degree or two of a horizontal sight along the bedding plane. And here's the horizon line. And if you need to move the phone, tilt the phone up or down, it will show you an arrow showing you which way you need to tilt the phone to get a level sight, and so on. And I'll show you another example of augmented reality from GMDE, a new feature that's going into GMDE. So the third phase is real-time computation in the field. And here are two examples. You've already, I think, seen Strabo tools. This is bringing real-time image analysis to the field and helping us be much more systematic about how we describe rocks and things like that. And GMDE Mobile, which I'll show you here in a minute, demo here for you in a minute, which does all of these functions. And it can do them because GMDE Mobile not only provides us with horizontal location, X and Y, with the GPS in the device, but because you can upload an offline digital elevation model, you also have Z. And when you have X, Y, and Z, you can do all sorts of interesting calculations. So there's a new calculation that the next version of GMDE will use, and I'll just show you a screenshot of it next before going to the demo, which is a rangefinder function in GMDE. So here's the rangefinder view that'll be in the next version of GMDE. It turns out when you have an online digital elevation model, you can simply, if you know the azimuth and the inclination of the line of sight, which if you're using the device, you can, the device can give you directly, or if you have prefer to use your Brunton compass to do a bearing and an inclination and so on, you can actually type those in. You can calculate the range to anything that is within the digital elevation model that you have, because you know where you are and you know what the shape of the land is, so you know exactly where the line of sight intersects the land surface. And this gives you both change in horizontal and the change in vertical from your current position, as well as the distance over the slope and so on. And that's an example of the type of calculation that you can now do in the field. And I show you these because I'm going to demo the programs for you using what's known as the simulator, which is a iOS programmer's device or program which allows programmers to show what the program will look like on the device without actually running it on the device. And that way I don't have to try to plug and unplug devices from cables and switch screens and things like that. I can show you both Stereonet mobile on the left and GMDE mobile on the right. So the first thing you'll want to do if you're going to be using these in the field is to turn on StraboSpot integration. And in Stereonet mobile, the way you do that is to click the info, bring up the info screen here, scroll down to the bottom, and make sure that this switch right here, StraboSpot integration, is turned on. In GMDE mobile, you come up under the project tab right here, you go to settings, and in this central panel down here, you scroll down to here, and again, make sure that StraboSpot integration is turned on. This is what allows you to upload to the StraboSpot database, and it also allows you to use the StraboSpot vocabulary or lexicon of terms that the database recognizes and so on. Unfortunately, using the simulator, I can't actually give you a demo of using the orientation of the phone to collect data. You do that by turning on the auto switch, and it shows you a not very interesting strike and dip here. I did want to say that turning on an automatic observation also turns on the GPS receiver, because the phone has to know where it is in order to calculate the magnetic declination and give you a true north reading rather than a magnetic north reading. So if you've ever wondered why it does that, that's the main reason. Another tip, if you're using this to collect data in auto mode, is that if you tap the screen anywhere in the area of the Stereonet, which shows, it freezes the measurement. And this is useful, for example, if you're saying, taking a reading on the underside of a bedding or something like that, where you can't actually see the face of the device, you can tap this to freeze the measurement, and then bring up the phone where you can see it and inspect it to see whether the statistics are what you would want, and so on, to record. All right, for the demo here, we're just going to enter data by tapping and dragging in the Stereonet. You can see when you do that, it actually rotates the Stereonet grid. This can be useful for teaching purposes, and so on, to show how great circles relate to the Stereonet grid and so on. And once you release it, you get a strike and dip. You can also tap and just type numbers into these two boxes if you want to enter data completely manually. Now I could just tap save here, but what I'm going to do is to assign a data type other than bedding to this, and we do that by tapping this button, which shows you the current bedding type, or planar data type. And these are the built-in data types, but I can define any one I want. And in this case, I'll click New, and then tap up here, and let's call it myelinitic foliation. And hopefully I spelled it right, but you can adjust the color that it uses and everything else with the red, green, blue slider bars. You can also pick one of 3 different line types to represent the great circle. And when you're done, you click Done. That's now selected. By the way, the zeros here mean that's the number of observations of each type. And when I click Done, it now says myelinitic foliation here, and I can turn on GPS so that I record the GPS here and click Save. Then I can just enter as much data as I want, and so on. But normally what you're going to want to do is to add additional information to individual measurements. And you could do that by tapping the data button here, which would take you to the data list, and then finding the observation and tapping that to go to the data details. But there is a shortcut. there's a hidden button over here under the strike or the trend label. It says trend if you're doing lines, strike for planes. And if you simply double tap in this area, it will take you directly to the datum details screen of the most recent measurement, bypassing a couple of screens and taps and so on. And of course, you can tap in notes and type in whatever notes that you write. Many of you may have noticed that on iOS devices, there's a little microphone on the keyboard display. And if you tap that, you can actually dictate your notes rather than type them. That works even if you're offline, don't have any internet connection at all. It still does basic speech recognition, although don't expect it to be perfect on technical terms and formation names and so on, but it could save you a fair amount of time. The main reason for showing you this screen, though, is to two things. First of all, if I tap the map button down here, I actually get to see where that location is on a satellite image. And if the image is dark like this slider down here increases the translucency of the image, so you can see all of your data regardless of what color you have chosen for it, and so on. But the main reason for showing you this screen is the Strabo button. This is where you can go to enter your official formal Strabo terminology. But this is a foliation type. We can go down here to myelinitic foliation, and we can even go, put in a sense of motion, tap down here to give the width of the myelinite zone, let's say 2.5 meters or whatever it is. The length, if you want, you can change the quality with this slider. Maybe it's 4 and so on. And all of these choices are immediately recorded with the datum itself. And when we upload to Strabo, it recognizes all of these terms. So that's how we collect the data. I'm going to actually switch to another data set here just to show you a few other features. So I'm going to go to the data screen here. Here are 2 datums, by the way. You can slide these. If you slide it all the way to the right, you will delete the observation, or you can hide the observation. So you have to be a little bit judicious with your slides and so on. But I'm going to open a different data set here. I could bring in data on the clipboard, and you can do this, I believe, from the Strabo app, which I'm deeply appreciative to the Strabo team for implementing that. But in this case, I'm going to use a data set that I saved on into the documents folder already. And so here are the lines in that data set, and here are the planes in that data set. And you'll notice many of the lines are grayed out, and that's because we filtered out those observations. We go back to the Stereonet view here. You can see we have still several different data types. I'm going to actually go to the filter screen and turn off these plane types here, so that I only see now these black planes, and the pluses are the poles to those planes. I can do various analyses on those data. If I go to plot config, I can contour the lines. I can choose the lines data set with this little sort of Rolodex type control here. And I can do a cylindrical best fit. It shows me the eigenvalues and eigenvectors of that best fit, and so on. And when I go back to the Stereonet, I see it's all nicely contoured for me. And this line here is the profile plane of these folded beds. And here's the fold axis, best fitting fold axis right down there. So now if we go back to the data tab, eventually we want to upload this data to StraboSpot. And the way I do that is I simply click the Save button, and it gives me a choice. Do I want to save it locally on my device or to Strabo? Of course, you will want to save things locally, but in this case, this data set is already saved. So I'm just going to go to StraboSpot. And I've already entered my credentials here for my account at StraboSpot. And as long as the program is active in the memory of the machine, it will remember that. But if you're starting up the program for the first time, you will have to enter your credentials in this area here, and then this button will say login, so you'll need to do that. And here are a list of all my projects in Strabo. And you can see I've been doing a lot of testing, a dummy test project, yet another test project, and so on to perfect the upload. In this case, I'm going to upload these data to southeastern Idaho. So I would just tap this thing. I could, by the way, create an entirely new project within this Stereonet app by tapping in here, typing a name, hitting new project, and then it would be added to this list. But for the sake of time, I'm just going to tap here. And given the slow connection, it will take a little while, but eventually it says success. It's been uploaded to my account at StraboSpot. So that's the main way that you might want to use this. The one other thing that I want to point out is this button down here. This brings up the iOS sharing panel. And the iOS sharing panel is extremely useful for a number of reasons. And one particular unexpected one is, let's say you're in the field, offline, no internet connection, and you're collecting data with your iPhone, and you have GMDE mobile running on your iPad. Well, it turns out that with the Bluetooth connection between these two devices, I can send data from my phone to the iPad, and then I can import that data into here by using the sharing panel. I would bring up the sharing panel. There would be an airdrop thing. Unfortunately, in the simulator, airdrop doesn't show up, but there would be an airdrop icon. I would tap that and then choose my iPad, and then just send the data to the iPad. And the iPad would ask where I want to save it, usually in files or something like that, and you're good to go. So I've actually already done that and seeded this data set over to GMDE. So let's start with that. So this is the blank view of GMDE. And we already turned on StraboSpot integration. You can see that this button now exists in this sharing panel here. But what we need to do is bring in a map and bring in a digital elevation model. Digital elevation models have to be in grid float format. And there are many ways that you can get elevation models in grid float format as well. When you're in here, you can switch maps whenever you want. I can go back to the map tab at any type and choose, say, the geologic map of the area, or I can choose the topo map of the area. But let's go back and use the satellite image. These NAIP images, by the way, are available for the entire continental United States and give you satellite imagery at 1 meter resolution, which is pretty fabulous. And I have to thank Nathan Mimi for making me aware of them initially. He's converted me. So now we have our base map. In the project panel here, you've got basic functions like get location. I can come over here and tap anywhere in the map and it shows me latitude, longitude, elevation. I can do measurements by clicking and dragging, and you can see up in the upper right corner, it shows how long the azimuth and also the slope. We can calculate slope because we have elevation on board, and so on. If the map is a little dark, I can adjust the translucency with this slider, and so on. So let me go get the data from Stereonet Mobile to put into GMDE here. I put it into the Files app, and this happens to be the data set right here. And what you do is you just copy the entire data set to the system clipboard. And let's see if I get this right. Yep. Do copy, and then I can go back to GMDE. And because those are all orientations, they will show up. I'm going to enter them in the Orient tab of GMDE. GMDE, by the way, recognizes point observations or points of interest in this tab, orientations in this tab, and contacts in this tab. So we go to orientations and then just tap the Stereonet mobile thing, and there are all the orientations. They've come in. These, we can change the symbols for these that came in with foliations. So if we want, go to settings, select planes, bedding, we want a bar tick symbol, and let's give it a little bit lighter, easier to see color as well. And while I'm here, I'm going to change my contacts for bedding to a nice green color. Okay. So let's do actually one of Stereonet Mobile's signature, or GMDE Mobile's signature feature, which is actually doing a 3-point problem. In this case on bedding, but there are many cases where metamorphic foliations and things like that are beautifully expressed in detailed images like LiDAR images and so on. So you can do this just by clicking on 3 points. We go to the Orient tab, tap the 3-point button here, and then I know that this treed ridge here and this contact here is the contact between the Preuss and the stump formation. So I'm going to set 3 points on it. One there, and one right up here. And it's calculated the strike and dip. That is, if I like that, I can save the orientation, and it plots it at the middle point that I clicked right here, selected in yellow. And then I simply can go to contacts, well, that's selected, and go project from contact. And the iPad maps the contact for me based on the orientation. If I like that, I could simply go save contact. And you'll notice that it actually made 2 contacts, a little short one here and a long one. We can join those by clicking here, then click join and clicking the other one. And now it's joined those 2 into a single one. And I ought to give it a name, which is JS over JP, and save. And I'm going to make that bedding and save. And there's our contact. Do just one more to show you a couple of other things. We'll do another 3-point problem here on this whitish ridge is the Peterson limestone. And so we'll click right there. We'll click up here, and we'll click down here and record that orientation. Go to contacts, project from strike and dip, and it's mapped that contact as well. Then we'll save that. Now, one of the things I can do here, I can immediately calculate the thickness here by clicking thickness. It says tap an orientation on the first contact, so I'll tap that one right there. And then I just tap anywhere on the second contact. Doesn't have to be up or down dip. I can just go like that, and it tells me that the thickness between those 2 layers is 255 meters. Okay, with that in hand, I can do other interesting things. I can draw a profile across here, and it projects the strikes and dips and the contacts on the profile. It's showing him in vertically exaggerated, but we'll change it down here. And that's useful. Let's say I know that this swale right in here is the location of another contact. I can mark a POI by clicking and dragging here. You see a little red plus going along, and let's say I know it's right there. And then when I close the profile, it's actually plotted that point on the map itself where the profile crossed it. Now, one final thing, and then I'll stop, is turning on the virtual GPS receiver in the simulator here. It says I'm on this ridge here. Let's say I'm looking over in this area here, and for some reason I want to plot a contact right on this horizon. Of course, with a good satellite image, that's easy to do, but we can also in the field take an azimuth and an inclination, or a bearing and an inclination. So we can go to Orient Rangefinder, which is not publicly available yet, but will be in the next one. My eye height is 1.6 meters, and the azimuth is 350, and the inclination is minus 14 degrees. And then when I hit save as POI and go back to the map, it's plotted the point right here. We can zoom in a little bit. Here's the point that I took that site on. That's the point on the ground that corresponds to that site. So I think, oh, actually, one final thing, uploading to StraboSpot, just like Stereonet, you click this button. So you come in here, you enter your credentials, and once you log in, your projects will show in this table. And in GMDE Mobile, you can upload all data, or just point observations, or just orientations, or just contacts. And you just tap the project that you want them to go to, or you add a new project, which will appear here after you log in, and you're good to go. All right, I think that's everything I wanted to show you about these two programs, and hope that was useful.
That was great, Rick. Thank you very much. Do we have questions for Rick? I think we should just stop and make sure we have the questions. Terry, do you want to just turn your microphone on and ask those questions?
Well, mine was pretty simple. I just wondered if you have if there's a tool to limit the distance you project those contacts, so you don't have to, or you just have to edit out things.
So I can show you that easily enough, because this one contact, actually this one that I just entered in here, actually crosses, oops, I'm going to save it first, crosses a fault which goes through this little valley here. We know that because I projected this contact, and yet the Peterson limestone is up here. Here's the Peterson limestone hogback. So now with that contact projected, I can click lasso and just draw a circle around the vertices which are incorrect or incorrectly mapped. They're selected, and I just go delete, and they should be gone, and they're not. So let's try that again. Not very impressive demo, but it does work usually. Yeah, there we go. Yeah, so you can, just like you can join contacts, you can also edit out vertices and so on, just by circling the ones you don't want with the lasso tool, and so on. I should say one other thing you can do with the lasso tool. Let's say you've drawn a contact by hand, which you can do just by clicking the draw symbol here. If I click lasso here and I just circle some of the vertices of the contact that I've drawn, I can actually calculate the strike and dip from the selected vertices. So this button verts to S and D. I click that, and it tells me what the best fit statistics are, and it has been a new strike and dip symbol which is calculated from a best fit to those multiple vertices. You can think of this as a 3+ point problem because in this case we're using a lot more than 3 points to calculate a strike and dip. So if you're suspicious of contact projection, you can draw your own contacts and then get the average or best fitting strike and dip from the vertices of the drawn contacts.
One more question was, when you upload the data, did they get imported as new or existing spots in StraboSpot? Rick, you might not know the answer to that.
So when you upload them, they get uploaded as a new data set to an existing project or to a new project if you choose to define a new project. So they will be new spots in either an existing project or in a new data set in an existing project. Did I say that right? I think I did. Yeah, they're always uploaded as new things. They don't overwrite any data ever. So, you don't have to worry about overwriting anything. I purposely kept managing your StraboSpot account projects and things like that to a minimum. And right now, these programs are only upload clients, one-way clients. That is, you can upload data, you can't download data. One of my projects in continuing isolation is to implement downloading of data sets from StraboSpot accounts to Stereonet mobile and eventually to GMDE mobile as well.
Right, and then one last quick question was, what's the source of the satellite images? Because they look so good.
So the satellite images here are NAIP tiles, Terry probably knows it better than I do, NAIP, National Agricultural Information Program or something like that. They cover all of the continental US and probably Alaska, although I'm not familiar with that. And they are 1 meter resolution. And actually, if you look at it, these are the images that Apple uses in the satellite view, in their satellite view. They're really great images and they have wonderful detail. I should say, by the way, maps in GMDE are entered as MB tiles. There are several commercial and a few freeware programs that can produce MB tiles. There's actually in the user's manual for GMDE mobile, there's a workflow that Nathan Nemi actually sent me to convert after you've downloaded the NAIP tiles to use the freeware GDAL software to convert NAIP tiles to MB tiles format. So all three of these maps, as you see, they have the suffix MB tiles on them. That's MB tiles is a way, if you're not familiar, here's the geologic map and our remapped contacts on top of it. The MB tiles are a way of showing large raster images on devices with small amounts of memory by dividing any map up into MB tiles. So this geologic map, for example, standard 7.5 minute quadrangle, has about 13,000 tiles in it of different scales and sizes, which are all managed in a SQL-like database and packaged in this MB tiles format. You do have to use GMDE mobile, you do have to master producing MB tiles. And I used a commercial program called MapTiler, which isn't all that expensive and is very easy and user-friendly and so on. But there are other freeware alternatives. Oh, I forgot one other thing. This button gives you a full screen view. But there you go.
Rick, this is great. You might take a look in the comments on Zoom and just see if there's any better explanations you can give that have been provided. But in the interest of time, I'm going to have us keep moving. And
Sure.
again, thank you very much for showing us this.
Yeah. Well, thank you for the invitation. I will, I'll stop sharing my screen now and mute my mic. I'll look at the comments, and if there's any I can answer, I'll just answer them right in the comments. Okay?
Great. Perfect. Thank you very much.
Thanks,
All
Rick.
right, guys. All right, bye-bye.
Bye.
Doug, can you maybe go on and do the data
Let me get
management issues?
yeah, let me get the right screen going here. And so is everybody seeing a nice screen now?
Yeah, that's psychedelic.
Psychedelic. So yeah, this is kind of the data back end, but just another, there are a lot of uses for Strabo tools, including a lot of animal uses if you want. Anyway, what I thought I'd be talking about today was what I am talking about today is the data structure and where Strabo sits with all this. There's a common term in data science and in marketing, in fact, about the long tail. And basically what the long tail is referring to is there are some things that are incredibly common that most people will have access to or need or want, like Ford Focuses. And then there is very highly specialized items such as an Aston Martin 177, where there's only about a handful of these made a year, whereas there are millions and millions of, well, there used to be millions and millions of Ford Focuses. What this extends to in data is looking at geologic features and geologic things. And I want to use a slightly different example because I think everybody can appreciate this. If we look at a map of earthquakes around the Ring of Fire in the Pacific, we all have a feel for what this means, where the earthquakes come from. But all of those data, all that information comes in at some point from seismic data that a seismologist looks at. And this is the seismic data for the Great Sumatra earthquake of 2012. And this sort of data to most people won't mean a lot, but is incredibly important for fixing any of those dots, position, magnitude, et cetera, that we see. What's a little more accessible to most users would be something like this, where we have a cross-section through the Earth showing some focal mechanisms, showing locations of earthquakes, depth, etc., and projected on this. And this is much more accessible for most people to look at and understand. And then finally, sometime we turn this into a final product like this from Tessa Graphics of a subduction zone going down, and that's based in part on the middle diagram, which is based on the lower right diagram. So basically going through what most people will see will be the cross-section of subduction. Less people, but still significant, will see the seismic, the cross-section based on earthquakes, and then finally a few people might want to look at the earthquakes themselves. So basically when we look at geologic data, it sits in some kind of spectrum of this, and we have geologic maps. This is a portion of a detailed geologic map that Joe Andrew made. It's on Strabo. But it represents a fairly complex data set. There are points, lines, and polygons. There's topography, observations. And typically we put these in as paper maps, a field notebook, and that makes them really hard to share and hard to integrate. So the typical geologist going out and collecting this in very much just analog form has a hard time sharing this. And what we want to do is take that data that sits out very far on the long tail and understand how we would move that easily into something that most people could see. For example, this GSA USGS map of North America. And so, you know, this map is based on countless studies of this sort that we put together. So how do we move that effectively up, and how do we effectively serve the long tail? Now, a lot of that's going to require collecting data digitally, and that's what this whole webinar has been about so far. We saw with Rick Almdinger's presentation just wonderful tools for collecting this. And this has been a long time coming. He did a very nice job on reviewing kind of the progress. And this is where we've sat for a long time. Kind of the practical way of getting our information in is using a GIS. And this is just an example of ArcMap by Esri. Few years old, but basically putting in information and putting in attributes about the information. So example, faulted contacts, types of contacts. And we can see up here that we can have all sorts of different things with faults, points, bedding measurements, fold traces, etc. And all of this is moving it into a digital format that we can classify and then convey. And when we convey that data, we're usually talking about conveying a database. And just a few definitions of what a database is. Here, we all have our ideas of this, but it basically means we're putting in the information digitally so that we can then share it easily with someone else and they can use it. There's a lot of barriers to that, but we'll just keep pushing ahead here. The typical way that we built these in the past, when we go back in time to the 70s or 80s or 90s, is as a flat file. And this should be very familiar to everybody from Excel. This is the sort of thing we find in publications, you know, a sample name, maybe a unique identifier, and then some data about it. And this table, of course, tells us a lot of vital information about the measurements, but it doesn't really tell us very much about what was done, where it was done, how it was done. A lot of times that sort of information, which we'll call metadata at this point, sits in the bottom of the table or in the text. But we could think about associating that metadata in a table as well, so that for every measurement, we have a lab and some information about that. They're really critical to using the data. One of the things that happens here, and the reason you don't see big tables of metadata in papers, is much of it's really, really redundant between samples. If you started putting all of this in your database, it'd really expand, and it'd be unwieldy to associate necessarily all these things with single samples. So one of the ways that we've gotten around that is a relational database approach. And I think everybody has this idea of, okay, we have values that are done by a certain method. Those methods then we can describe. We only have to describe the method once. We only have to describe the value once. And basically we end up putting together multiple tables that are related by these numbers in green here, which are a key that goes from table to table. And that's been the typical relational database approach that we've taken for a long time. And most databases you come online are done this way. Tables and keys, where you go from a method to a lab to its information. And we go across all these tables, hopefully showing only data once and joining them together by these numbers, so that if you ever wanted to go from this item measured here to the lab address, you could do it through this intermediate method table. Now, these are put into relational database, and that means the structure here is pretty rigid. Relational in this sense isn't because we're relating tables to other tables. That's part of it for us, but really it's based on relational algebra. Basically you're writing out equations that tell you what to do with the data and what to do with the various entries. This is really rigid. It's very hard to change. It can easily be broken. You can break relations between the two of them. And the schemas tend to become really pretty large and sometimes unwieldy. So this is the NAVDAT EarthChem schema for geochemical data. And you can see that this is just a whole lot of different tables, a whole lot of places. So basically we could go from a sample and work our way through eventually to some other factor on the other side of the table, but we'd have to go through a whole lot of different tables to do this. The process of going through these red features here that you see in here are the links. Sorry, the red triangles are the links going from table to table is called a join. And basically, joins can be just a pain to go through. It's just a nightmare because sometimes they take very long to go through. They can have very poor performance issues, and just kind of understanding relationships can be difficult. So in Strabo, what we've gone to, and Basil introduced this the first day, a graph system where essentially observations are nodes or points on the graph, and those observations have relationships to each other. I'm not going to go through this in too much detail since Basil did this already. But it's a very flexible approach, and it means when we add data, we just throw another node in and we add information about it. Now that information is in a controlled vocabulary, but we can add and change it very easily. The nice thing about the graph approach is that we can get from data to attribute and data to data pretty quickly. So if you think about this y-axis over here being the number of joins or the number of jumps we have to take through the data, we can compare relational databases to graph databases, and Neo4j is the one that we use in this system. But relational databases, after you get past 2, 3, 4 tables, essentially really bog down. The join operation is extremely slow. So for example, with 5 joins and 1 million records, you never get a result in this case. Whereas going through a graph, the performance is really quite spectacular. Getting through segmentation of it is quite quick. So that's again a very much a good approach or a good aspect of the graph system. As I said, we still have some rules. They're not as stringent, or changing them doesn't break everything. But for example, we do have a lexicon. So a dominant full geometry will have some kind of standard definitions, standard vocabulary. And then we always allow unknown and others in all of these, and you saw that the other day. The way we store these, and sort of the analogy for data storage to the relational database, is something we call JSON or JSON, JavaScript Object Notation. And all of this it's another way of describing information. We use a flavor of this called GeoJSON that is nicely tuned for bringing in geographic information. It has its own specification, which is nice. But basically what we have are features, strikes and dips, contacts, whatever the feature is, and it's represented by some data and some information. JSON is a very nice language, although this looks horrible. This is actually fairly readable. It's not binary, it's all ASCII in format. It still looks pretty complicated. And to most people, you would look at this and go, okay, yeah, I can find words in there I recognize. Modified timestamp, I think I know what that is. But then there are other things in here that are a little less clear. But the thing about JSON, GeoJSON, and some of these formats, they're basically like HTML. You can specify it and everybody knows how to read it. So JSON is pretty much in this genre of way of communicating data. And this is the first big data set I came on. It's actually by a guy at KU with me, Mike Taylor, who posted some active tectonics for the Andes and the Himalayas onto GitHub. Most of you will think about GitHub as a core repository and versioning software. I know that Mike uploaded this in GeoJSON format. I don't think, I'm pretty sure, I'm sure he didn't know what that meant. But even though he didn't, everybody who's a programmer, everybody working on GitHub does. So this is his map of the Andes in GitHub. This is actually the GitHub image. And his fault map where you have fault names and other information about it. So basically, Mike didn't need to know anything about JSON. The JSON programmers and readers didn't need to know anything about geology, and it all reads in very, very easily. So that works because in part of the standard of the language, but also because of web services. And when Rick was talking about his Strabo upload, he's utilizing web services at Strabo where he can upload data. And basically, it's very simple communication between the client and the database through an application programming interface. That's all very well specified and very open and easy for people to use. One of the things that we're trying to do with this, and you've heard about earlier in the week, was trying to build off of FAIR data principles: findable, accessible, interoperable, and reusable. Findable, you've seen the search interface. Accessible, you've seen results from that. Interoperable, I think the JSON example we went through just shows you how interoperable you can make these data. And then reusable, if you've done these things, people can grab them and use them again. So these are all points that we're trying to move towards. These are all goals that we have. StraboSpot is built on the idea of FAIR data, that all of these can happen. The search to download, you serve it in JSON or GIS, and you get the full metadata so you understand what people meant. So that's all quite important to being fair. The interoperable part, we've talked about this a little bit. Data from Strabo can come in as shape files, KMZs, so GIS, Google Earth, Stereonet, Fieldbook, and Strat sections. This is the Fieldbook view. I've talked about this before, basically exporting to a PDF so that everybody can see what your spots are like. This is just a Strabo data set in KMZ put straight into Google Earth with all the data about it. And then finally, this is some Stereonet, a Stereonet representation of Strabo data. Again, we just had the demo on this showing how easy that connection was. So what we're trying to do with StraboSpot and what we're trying to serve here is taking up the very long tail, kind of sweeping up the really more specific detritus, if you want to call it that, coming out of the science. But this is really, really important because everything that's based beyond that is based on the very specific information that we have. So trying to package that so it's fair and making it accessible both in terms of being available online, but accessible in that you can put in enough information to really document what you've done and have other people understand it. So that's just a quick presentation about the data structure and thinking about StraboSpot as data. I think I'll stop there.
That's great, Doug. Thank you very much for doing that.
Yep.
And what I'm going to suggest is that we take a 5-minute break starting now. If people, so we'll start at, whatever, 7 minutes past the hour. If people want to ask Doug questions while we're doing that, that's great. And then we will reconvene and talk about projects. So let's go with that motif. So 5-minute break now, and ask Doug questions if you want. And feel free to unmute as well.
Or Rick. Oh, Rick's off now. Okay. Well, Basil, I think I'm going to take a quick break here for just a minute too then.
right, Randy, it looks like you got some people sending in some projects for you.
Can I make a quick announcement first?
Of course.
Sure.
So over the break, I contacted Jason Ash, and the next version of StraboSpot will have the NAIP tile server integrated into it.
That was
Ask
fast.
and you shall receive.
Ask and you shall receive.
No, that was great. The other thing that the voice functionality is something we'll have to talk about. We've been on the assumption that there's just no chance of doing that in the field because of the lag time and also just wind noise. But we'll at least look into how difficult that would be given the new information we have. So it's one of these things. It's a very evolving sort of situation. I'm going to go ahead and start now. I just want to remind people who came on a little bit late, we had to switch the program around to let Rick go first. So we're now going to go through the user demonstrations. I'm going to hold these to 30 minutes. I know there's a lot of good stuff here, but I want to make sure that we hit the Strabo 2 stuff at the end. And then I'm going to send out a short poll. It's only 10 questions at the end, and I'll put that in the chat box, but it'd be nice while you're still around to do that, and if not, we'll send it out to the emails as well. So I would say, Randy, let's take it away and see what people manage to do in a couple days.
Yeah, sure. So I'm just going to say a few quick words and then get out of the way because we don't have much time. I just want to say thanks to everybody who submitted the project for this. We were super happy with them. Everything looks great. The projects we're going to show today are basically just representing kind of a good diversity of sort of research topic and functionality used in Strabo and geographic location, which is to say if your project didn't make it onto this list for presentation today, that's no reflection of the quality at all. It's just a reflection of the amount of time that we have in trying to cover sort of a decent amount of ground. So we're going to go ahead and get started with these. I'll say to the presenters, just give me a heads up when you want a slide advance, and the name, the order of the names on the screen right now is the order of the slides that are going to show up in the slide deck. So we are going to start with Diana Zek. And just go ahead and unmute yourself when your time is up and just take it away.
Hey. Hi, this is Diana. Thanks, everybody. So I am just going to quickly tell you what we've been working on this week. So this is a project that we have been doing for a few years, and then this workshop gave us a chance to try to put it onto StraboSpot. So here we're really interested in looking at some detailed structural and geochemical work along the southern Iberian shear zone, which is in southwest Spain. So the group in the middle, myself, former master's student Cheryl Stevenson, and then my colleagues Manuel Diaz-Asperoff and Carlos Fernandez were really kind of the ones collecting the data. But then we also use this workshop to get other students involved. So Nancy Duque in the upper left corner, she's been working on kind of the subsequent part of this project. And then the three students not shown here with the smiley faces, they're gonna be brand new master's students in fall. So we also use this as a chance to kind of all get to work together, because in many cases we haven't actually met in person yet. So that's due to the COVID crisis. So that's been a nice feature. Okay, move please. Next slide, Randy. Yeah, so this project, like I mentioned, has been, some of it's been published, and the upper right corner shows kind of typically like a publication figure that we have. So as of now, this is kind of how anybody could get the data. You know, kind of a typical publication where we have a map showing where we are, and then a whole bunch of measurements all put together in a Stereonet. But we wanted to do something, obviously put it in Strabo to make that data more accessible. So our project is just studying the impact of fluids during deformation of a ductile shear zone. So the data sets we are looking at are structural fabrics we use for the kinematic study. There are some cool lithological changes. These are metabasite rocks that have a retrograde metamorphism related to the shear zone, as well as some major element geochemistry. So our main goals during this workshop was to learn how to use StraboSpot for future field work, because there's another big phase of the project moving forward. We're also trying to input data from the previous field work to see how that works. And like I said, the other underlying goal was to meet the new members of our team and kind of get a chance to work together. Next slide, please. So what we accomplished this week, everybody did just a little bit. So we managed to put 88 spots in. Each one of those relates to an outcrop. So you can see kind of the map here. So this is kind of overlaying our existing map. And so we have a lot of data in these transects where we took geochemical data. All of those outcrops, we have lithological tags with kind of the main formation, but also kind of its subdomain related to those metamorphic changes. A lot of foliation lineation fabrics, but we have tons more photos for a lot of the outcrops. And then we also kind of played around with putting CSV files attached that show the major element geochemistry. And then I had fun learning Map Warper, taking 2 of those published map and georeferencing those. So you can see kind of where that is. So this is just zooming in, showing that spot. So, oh, go ahead, keep going. So lessons learned. So on this project alone, we have way more data that we could add, microstructural data, field sketches, etc. The current maps there, I just did quickly from our published maps, but they could be georeferenced better, but it was kind of neat to see how well I could get them without much effort to work on Map Warper. But the big thing that I think we want to think of as we move forward with our next phase of our project, where we actually want to use Strabo in the field, is we need to give considerable thought, and I've done this a little bit, about how we'll scaffold the next phase of the project. So I'd love to hear people's experiences with this. So we have a big group of people that are involved in the next phase. So there'll be 4 faculty, 6 graduate students, and it's funded by the NSF IRIS. So there's a lot of undergraduate students involved. And there'll be more types of data, including laser scanning, et cetera. And so thinking about how to scaffold that, and the biggest part I've been thinking about is how to reconcile that. Really, we're trying to use StraboSpot for a dual purpose. We're using it as a digital field notebook, but we're also using it as a way to share data. And because I've been working analog my whole career, thinking about having everything in my digital notebook available, and as well as every one of my students on the project, is not something you necessarily want to share everything. So trying to decide how to scaffold it the right way so you don't have to share every undergraduate field measurement, but you can still share all the data you want to. So I'd love to hear people's recommendations on how to make all those pieces work together in Strabo. That's it. Thanks.
Okay, thank you, Diana. I think for the sake of time, we're probably not going to have time for questions for each of the individual presenters. So we're just going to go ahead and move on to Matt Dorsey at Texas A&M. Take it away whenever you're ready, Matt.
All right, can everyone hear me?
Yes, we can.
Okay, perfect. All right, thank you, Randy. I appreciate the opportunity to share what I'm working on and welcome any feedback. Oops, I had some issues there. And so if you have feedback at the end, you can chat me or get in contact with me. I'm currently a PhD student at Texas A&M, and I'm currently using StraboSpot to organize data that we collected in the field last summer along the Punch Bowl Fault zone in Southern California. So if you're not familiar with the Punch Bowl Fault is an ancient exhumed strand of the San Andreas, and it's labeled PF here on this slide, just to the south of the active trace of the San Andreas. Deformation of the Punch Bowl sandstone, which is seen here as an obvious plunging syncline, has been well studied by my advisor, Judy Chester, and others. But the goal of my current research is to characterize older and deeper seismic deformation within the crystalline basement complex. You can go to the next slide. Okay, so for this project, the focus has been on a few key outcrops. Therefore, the main utility of Strabo, in my case, has been cataloging samples, photographs, orientations, and other data at the outcrop scale. We're going to go ahead and take a closer look at the highlighted spot, outcrop DP6S here along the obvious trace of the Punch Bowl Fault. Next slide. Thank you. So using a photo that shows the key portions of this outcrop, I then broke the outcrop into polygon spots, which I call grids 1 through 10 pictured here. These represent more focused images that show more detail. This outcrop here is about 8 meters wide and about 2 meters high. And what you're looking at is two fault cores containing ultracataclysite, which are the dark brown colors on either end of the image, and then in between the two fault cores is what we categorize as a foliated cataclysite. So now we're going to go ahead and take a look at what is actually nested within just grid 1, which is highlighted here. So within grid 1 are spots marked as polygons or points indicating sample locations, orientations in the outcrop, and other points of interest, like maybe I took a Munsell color reading on certain portions of the ultracataclysite. Each box here in this photograph is 10 by 10 centimeters. And so opening the spots nested here yields more information on individual samples or points of interest. I also am planning to use Strabo to log sample progress in the lab and integrate Strabo microdata in the future. My opinion is that this is very useful for being able to quickly review the context of individual samples within an outcrop. Next slide. So my impressions are overwhelmingly positive. I think Strabo provides a clean and efficient way to record data and observations at the outcrop scale. And I think a lot of the focus has been on mapping large geographic areas, but I think it's also very useful for using image-based maps and plotting sample locations and things like that. Here you can see my digitized hand-drawn map of the particular outcrop that I showed you. This would be, in my opinion, really difficult to produce digitally as a digital sketch. So I produced this by hand and then turned it into a digital sketch. But I do think that recording sample locations and measurements by hand gets really messy. Things get really jumbled and hard to read in the end. And so I think that this is where Strabo comes in. I think it'd be really useful to record sample locations and orientations and things in the field. So that's about all I have. I just want to thanks again to all the workshop hosts for introducing StraboSpot, and I think it is an awesome tool to use in the future.
Okay, thank you for that contribution, Matt. We're going to move on to Brian Platt at U Mississippi. So take it away whenever you're ready, Brian.
Okay, thank you. My slides aren't as well organized, I think, as the previous ones, but when I started this workshop, my first thought was to try and apply StraboSpot to our field camp area in the Arbuckles in south central Oklahoma. And so my colleagues and I, since we have to go out there every summer, we thought, well, we should probably start doing some research there. So one of the first things that was done in one of the areas, we have our students map, which you can see here outlined by the brown line, the extent of the field camp mapping area. We had a master student map this area and quite a bit more to the north, and that allowed us to use his work as an answer key. And in the interest of continuing with this answer key, I thought I would put his information into Strabo, so I used Map Warper with it to digitize and georeference his thesis map, and then I entered the data, strikes, dips, and faults, and contacts, and so that's what you're seeing here, and his thesis map is overlaid there with some transparency to it, and so that was done in 2017. And with our students, I wanted to look at the maps that our students have made, because we've been doing this for several years now, and see if by plotting up all of their measurements, we could identify places where the students are having problems, where there's a lot of disagreement about the locations of faults, and where the students are all in agreement and thinking, well, that's probably a better expression of that fault in particular. I was going to do it with contacts and strikes and dips, but it was starting to take too long. So I decided just to focus on the three faults, the three northwest, southeast oriented faults that in this map are plotted as known faults. So they're the solid red. Can we go to the next slide, please? Thank you. And so I created a data set for each of 5 different student groups that we had who mapped the area in 2019. And these are all those layers are on right now, and so you can see the lines all over the place. And I've circled the areas where, you know, that where the fault location, most of the students agree with the location. And then I've circled an area where I think, oh, we really need to work with the students more in this particular area because they are not, you know, getting the proper orientations here. And also, you know, I've spent probably a total of 6 days in this field area. So, you know, I haven't had that much time to go out and work out an answer key myself. So in addition to the thesis student, I would like to identify some areas where, you know, you have good expressions of contacts, bedding, and I'm hoping this could identify those areas so I could specifically go back to those areas in future summers. And then, let's see, from my last slide, there are other research projects that we've sort of branched out into. And this is one example where in the area here, I've sort of zoomed in on the eastern part of the mapping area. This follows Honey Creek, right by Turner Falls State Park here. And we have mapped out these different tufa exposures, and we're looking at Pleistocene versus Holocene tufas and doing some geochemistry on them with one master student right now and hopefully another student in the future. And so I attempted to trace out using the polygon some of the areas where we had good exposures of tufa, and this is going to be really important to pinpoint where we got our samples from. And so I have here a spot that contains a photograph of a sample in float. We do have thin sections, but I didn't have the images to put them in the sample image. But I can definitely see the utility for that in the future, because for this project in particular, it will be very important to pinpoint exactly where our samples came from, because in many cases in the field, you really can't differentiate between the different tufas. And our student presented this at the Mississippi Academy of Sciences meeting in February. And I think that's all that I have. Thank you.
Okay, thanks, Brian. And moving right along, we have, I think Ben is going to present this, but this was a project done by Ben and Noah and Yvette Kuiper at Mines. So take it away whenever you're ready, Ben or Noah.
Perfect, thank you. Yeah, no, it's both Noah and I are here today. My name is Ben Magnan. I am an incoming master's student at Colorado School of Mines.
And I'm Noah Fleischer. I'm also incoming master's, well, not incoming, I just started, but a master's student at School of Mines with under Dr. Yvette Kuiper. And so we're going to talk about our mapping project that we did with this. So if you could go to the next slide, Ben will take it away.
Yeah, and I also wanted to say this project is actually the master's project of Dustin Shockley, another master's student under Yvette. And he let me come out in the field with him this summer since field camp was canceled and put online. So all that you're going to be seeing today is this data that I collected with him out in the field. And so we decided to use Strabo just to kind of show a little location map. You can see most of the data points are located a little bit southwest of Idaho Springs in the Front Ranges. And it is well known just mainly for the silver mineralization along the Montezuma Shear Zone. And you can see a picture on the right of the Montezuma District. And in the bottom right of that image, you can kind of see the Montezuma Shear Zone moving through. And with some further field observations, we're kind of coming to the conclusion that there doesn't really seem to be much of a shear zone there. And so this is kind of an evolving project with new questions being raised of what exactly is controlling the mineralization if the Montezuma Shear Zone isn't there. So if you go to the next slide, you can see some of the data points that we were able to bring into Strabo.
Yeah, and so basically what we did is with Ben's field notes, we incorporated that data into StraboSpot and just mapped it out and kind of got a basic idea of what we did. So foliations, lineations, fractures, contacts, and folds are the primary data that we had. Overall, we came to a couple conclusions, and obviously with such a small data set, you know, these are very approximate, and they're just possibilities at this point rather than conclusions. But up in the top area, we see a potential fold hinge. You know, there's not much data there to back it up, but we're getting somewhere. Also, we see a biatate gneiss and monazite contact. That one is a little bit more conclusive because there's more data points throughout there. But this is not a complete data set. The project's just kind of getting going, and so there's a lot more to be done. And obviously, a better map will be produced. But you know, for the purpose of this workshop and the project, and also to get a better hand at using StraboSpot, we decided to throw the data in here, and looks pretty cool. So you can go to next slide.
Yeah, so we were trying to kind of use all parts of StraboSpot and importing images, annotating them a little bit. So here you can just see two pictures of some shear senses that we found out in the field. One of just some sheared veins, another of S&C fabric. So this gave us a good opportunity just to put in some diverse data into StraboSpot. But the cool part is what we did with the next slide. So if you move on, you can see that we use Strabo tools. And if you want to talk about that.
Yeah, so we just used the feature that was talked about in the workshop on Wednesday to get an idea about the lineation directions here. And so, and fabric directions. And so it's pretty nice. And we found, this picture was not taken necessarily with proper orientations in the field, but we decided just to kind of test the tool. And so this is actually the same picture from the last slide, or a very similar picture of the same rock in the last slide. But that tool, as you can see, is pretty darn effective. So we thought that was just kind of a nice thing to add in here to show, how it can be used. But of course, if we did this when we were actually in the field, it would be a little bit more effective. But overall, that's pretty much what we had. But this project was cool, and it'll be continuing on. But for me personally, my project is just getting going, and it was delayed because of COVID. And so next week, I'm actually going to be in the field in Connecticut doing some mapping. And, I plan to use StraboSpot and take quite a bit of measurements and use these tools, which this workshop showed. So, we just wanted to say we appreciate the workshop and having us present. It was a lot of fun doing this.
Okay, thanks Ben and Noah for that. With that, we're going to move on to Michael Frothingham, his project, also in Colorado. So Michael, if you're there, take it away whenever you are ready.
Okay, thank you very much. So yes, this is a project that I'm presenting. However, it is not my data. This on a project. This 6 Mile Fold is located between Boulder and Fort Collins. It's a very common mapping project for structural geology classes at University of Colorado for years. And I want to share this with all of you so that potentially you could use this public data set for teaching Stereonet, simple mapping, and virtual field courses. So there's a number of contributors. Again, it's not just myself that include my advisor, Kevin Mahan, and other graduate students and undergraduate students. So you can see where my map is in the state of Colorado on the map on the left. And then there's a zoom in, the satellite image of this fold you can see with the light gray layer. And the project is, we would take students out to map the Fort Hayes member limestone of the Niobrara Formation and look at bedding, satellites, contacts, faults, and folds. And then as the purpose of this is actually not only mapping, but also working with Stereonet as an introductory lab in structure, we want to look at the interpretations of both the deformation of these rocks and their fabrics, but also look at the relative timing of the deformation, specifically with the formation of the stalactites and the folding. Next slide, please. Okay, so there's a variety of spot types that we use. For the point spots, these include bedding and stalactites that you see on the left. And there's some other spots that we could collect as lines and as traces. These might be contacts or faults and folds that you can see on the right. And I'm going to show you what we do with this on the next slide, please. So on the top is a photo of some structural geology undergraduate students that we brought out to the field a couple years ago, back in the good old days. And what we had them do is we had them stand on one of the hinge areas of one of the folds that you can see on the left picture. And they stood on top of the bedding surfaces of this limestone. And we had them stick their hands up in the air, representing essentially the pull to the bedding plane around that fold. And I've extended their arms with little red arrows. And what we should all be able to see is that there's a variation, and we might be able to actually see we could see the fold as the students from the left are on one limb, in the middle might be closer to the hinge, and on the right might be on the opposite limb of this fold. So I guess qualitatively in the field, we could see the deformation of this limestone. But then if we wanted to actually move this into StraboSpot, and if we use the incorporation of Stereonet, and in this case I used Orient software, we were able to come up with some interesting results here. So we plotted this on a Stereonet. The poles to bedding are in light gray circles, and the poles to stylolite foliations are in black circles. And we're able to get fold axes from both of these. And what we can see is that there's a moderately south plunging fold axis from the bedding. And there's also a fairly similarly oriented, moderately south plunging fold axis for the stylolite. And the initial interpretation that we got from this for our structural geology class is that the stylolites seem to have formed either pre or syn to the folding. And this is a pretty simple interpretation that we get, and it's a really good project just to really get the students into Stereonet with a fairly well-behaved and simple database that still tells an important story. So what I'm hoping by presenting this to you today and by making this data set public is that maybe you can use something like this for either a virtual field course or as just an opportunity to help teach a little bit of field mapping with a really great exposure on the satellite imagery and these data points. And yeah, I mean, I'm hoping to share this with all of you. Thank you.
Okay, thanks, Michael. And Basil, it strikes me we have time for one more, yes?
Yes, definitely. Go for it.
Oh, okay. All right, with that, we will move on to Jochen Mesger, at the University of Alaska. Jochen, are you there?
Yeah, I'm here. Can you hear me?
Okay. Yes, we can hear you. Take it away.
So, yeah, I think when I thought about doing a project, I thought about digging up my old PhD stuff that I've done in the Yukon in the 90s. And because I did quite a 3 summers worth of mapping there, and all the data now resides in my 300+ page thesis, and none of it is digital. And it would just be a shame to lose it. And so this is an interesting area. So I'm working I used to work in the Southwest Yukon between the North America, ancestral North America, and the treated terrains. And yeah, I've got more than 600 stations, a lot of structural work, mapping, and also lots of thin sections to identify shear sense indicators, metamorphic parogenesis, assemblages, and I did some geochemical isotopic data. And I published in the 2000s, but even the data repository at that time didn't really exist, the digital one, so all would be lost. So I thought it would be a great idea for StraboSpot. Next slide, please. So I started working and plugging in about half of the data points, 300+, and you see the mess on the left side. But what it does show you, so this is all just a schist, and it shows a broad, very large regional empty form plunging to the southeast. So that's the red line, it's a trace of the fold axis. And that's just to the east of the Denali fault, that's the brown line. And I've used I didn't publish detailed geologic maps, so just the smaller ones and a large overview map. And so I used one that was published and warped it with, or rectified it with MapWarper, and I'm surprised how well my pre-digital map turned out to be. So so that's the one on the right side, overlaid the Mapbox topo. So it looks pretty well, and actually that worked perfectly. It took me just a couple of minutes per map, so that's really easy. Yeah, so next slide, please. So yeah, I've got a lot of structural data. So what I've done so far in this project in these couple of days, just enter the schistosity, lineation, and some fold axes. I hadn't had time to do extra data set, build an extra data set for the shear sense indicators. Of course, I can incorporate Stereonets. I've uploaded a couple of outcrop and thin section photos. So that's pretty handy because all this stuff is just resides on my computer right now. And it should be made available because that area is, even now, it's pretty neglected. When I looked at the search map yesterday, 2 days ago, there's really nothing in the, not much in Canada at all, and certainly nothing in the Yukon. So that should be changed. So last slide, please. And this just shows the insert map, like a detailed map of a structural section where I've overlain mineral isocrats. And I've done a lot of detailed sampling at that time. And so the StraboSpot would be ideal just to show the density of sampling, and also I could draw on the isocrats. And the nice thing is on the map, you're restricted to whatever scale you have. But of course, on something like StraboSpot, you can zoom in and you'd have more chance to get a little bit better chance to work more detailed, work out the iso maps or isocrats in more detail, and maybe do some cross sections. So yeah, there's great potential. I certainly will extend beyond what I've done so far and hopefully migrate all my data that I have that is on paper at this moment onto StraboSpot and make it publicly available. So I guess, so for terms of archiving, it's perfect. It's an ideal tool. And I thank you for the opportunity for me to do this and for giving me the incentive to do this. So, and that's all I have to say. Thank you very much.
Okay, thank you, Jochen. Just to elaborate on one of your points, that project is in fact the only public StraboSpot data point in the country of Canada right now. So thanks for that. Basil, we do have one more. My impression is we probably need to move on. Is that accurate, or do you want to do this?
That is correct. I think at this point we need to make sure that.
Okay. All right. Well, I'll just give a quick shout out to Jack Williams at Cardiff. Uploaded a really interesting project, a project that I'm relatively familiar with, looking at seismic hazards in the country of Malawi. So another first for Strabo. That's our first East African data point. So thank you for doing that, Jack.
Great. In fact, thank you all for doing that. It's been great. We will be in contact with you about that, and please leave those up and make them public when you can. And just also to follow up another point from Jochen's talk, which is that we're working with NSF that this will count as a data repository for structural geology. So this will satisfy National Science Foundation, and we're also working with European funding agencies for that. So we're hoping that this will kind of take off in that respect. But the one thing I would like to make sure we talk about is Nick Roberts was going to give us an introduction to Strabo 2, which is what's developed right now and also what we think we're going to be doing in the future to improve the StraboSpot field-based experience. Nick, go ahead and take it away.
Awesome. Can you hear me just fine?
Yes, we can.
Okay, great. So alongside the development of Strabo 1 and making a public-facing app, and as we have more users, one of the things that we've been working on is developing an iPad application that has an enhanced user interface for people going out into the field. And so I want to talk a little bit about that user interface and take 10 or 15 minutes to show you. I'm going to give you a demo of the structural geology portion of the app. It's in the final stages of development, so it's largely working. You'll see there's some graphic enhancement that we need to do, but it's basically done. And then I'll give you a little sneak peek of some screen grabs of mockups that we're doing to do a new sedimentology strat section builder in the same iPad application. And the goal for the design goals for the second iteration of the StraboSpot mobile app is that the map is always visible and is kind of the centerpiece of data collection. And the interface is more simple. And we specifically thought about incorporating flexibility in the user interface to accommodate different types of structural geology workflows. And I'll talk a little bit about that in the mockup. And then finally, we're including some better ways to actually collect that data rather than the form input that you see in Strabo 1, that it kind of speeds up the data collection. So with that, I'm going to switch over to my iPad. And this is the user interface for Strabo 2. So you can see I'm in Madison, Wisconsin at my home office, tiny apartment. And the map is basically always visible in this app. So I'll give you a little tour of how the app works. So in the top left is where all of the settings live. So information about your account, starting a new project, loading from server or loading from the device. Some information about the active project. I've preloaded a project that I'll show you a little bit later. And then the attributes like the spots and images and samples and tags. So this should be pretty familiar. And then the ability to have custom maps. So it's all here, similar to Strabo 1, a little bit reorganized. And then we have a layers tab where you can load custom maps, or you can view a few of the default base maps. And we have those same actions that Strabo 1 has. So the zoom to the extent of spots, save maps for offline use, add tags, and lasso for Stereonet. So all the functionality of Strabo 1 is here. And by the way, we are using the exact same data structure. So the project that I will show you a little bit later was collected during my PhD thesis on Strabo 1. So it's completely compatible. So to create a spot, we have those familiar tools. And if I create a point spot, a major difference between Strabo 1 and Strabo 2 is that data are all collected in a notebook page. So I have no measurements or photos or tags or notes yet, but I can add data to this notebook page and it will all be summarized in one place. If you want to edit the geometry, you can actually move this spot around on the map, or you can tap and change the latitude and longitude. And along the bottom are data collection tools. So viewed here, the photos and notes and samples. And so I'll maybe start by adding a sample. If I tap to add a sample, this view pops up, I can move it, and the whole time the map is still scannable. You can make sure that you're in the right place. And I can do a description. I can tell it something about the orientation. and save the sample. And the samples will come and the information about them is editable in this notebook. And if I go back here, one of the development glitches, the samples aren't showing up, but the samples would be viewed here. The measurement tool is similar. So I'm moving my iPad around right now. You can't see that, but you see that we have a live response strike and dip. And to take a measurement, I simply tap on the compass and it collects measurements, and those measurements populate the notebook. And one really cool thing that we've done is that you can, rather than identifying single features, you can actually identify all the features at once or select several and identify them. So I can say that those were all false and there were normal faults. And then that data gets stored. And if I return to the overview, then those measurements appear on the notebook page. There's one more aspect, which is that you can actually view all of the spots that you've collected by swiping from right to left. So you can quickly navigate to the nearby spots by just tapping on these, and they'll load the other spots. So it's a good way to keep track of where you've been, and they'll be highlighted on the map. So that is one way to input data, and that's a kind of, that's following a similar workflow to how Strabo 1 works. There's another way to input data more directly onto the map, and that's using something called shortcuts. So down here in preferences, I can go to shortcuts, and I'll just turn on the measurement shortcut. I can turn all these on. And these are basically ways to add data directly onto the map, and it creates the spot in the background, and you can edit the spot later. So if I click on the measurement tool, it pops up with the measurement tool, but notice the notebook does not open. And if I tap, it will create spots at my current location. So I can move around the map area, and every time I tap, it'll create a new spot at my current GPS location. But let's say I get to an outcrop that is actually really interesting, and I want to take several measurements there. I can just click down here at the bottom and go into that spot. And now if I can continue adding measurements to that spot and categorize and all that stuff. So this is a great way if you're doing a kind of more campaign style data approach. You can take pictures on the fly, you can take samples on the fly, and they'll create the spot structure in the background. So you don't need to be clicking through all those menus if you don't need to. And just like Strabo 1, we have the ability to do overlays, and then the last thing that I'll show you is I'm actually just gonna delete these spots so that I can, well, no. So I'm gonna take you to my PhD field area in Western Australia and just show you what it looks like when you pull in data from Strabo 1. It's all here. I can load up a geologic map. Looks like there's some delay. I can load up a geologic map that I imported of my data from Mapbox, and you can see all of the structural data that I collected in Strabo 1 is there. So this is fully compatible with that. Okay, so I'm going to stop sharing. I'm going to go back to the PowerPoint, and I will just finish up. I will finish up very quickly. Can you see the PowerPoint?
Yes, we can see the PowerPoint.
Okay, awesome. With the strat mode. So we're going to follow those basic design principles with the strat mode, and you'll be able to drag up to create new layers, and the entire Strabo vocabulary for stratigraphic data is located at the bottom of the notebook page. And you can view individual layers in the notebook. And we're going to add this feature that we're really excited about, which is actually dragging and dropping predefined data onto a strat column so that you don't, so things like sedimentary structures that are very common, you'll just be able to drag it and it will record its stratigraphic height or interval. And we will be able to toggle between the strat column view and the map view. So people who are doing kind of hybrid stratigraphic measurement, but also structural geology can toggle between those seamlessly. So yeah, so this is a community-based effort. You know, we as a design team and programmers and geologists need the impact have basically based all of this design on the questions and comments during workshops like this. And so we have been and will continue to reach out to the community throughout the design and development process.
Thank you, Nick. So I am going to send out right now a quick survey. It would be great if people could do that. I'll also, if you don't want to do it right now, I'll send it out later. That'll just help us know how to run these better in the future. I'd like to thank everybody. We've gone 2 hours on the last two. I want to thank people for sticking with us through that so that they could see, particularly what other people had done for this. So I guess I'll say I'm very pleased that that many people were interested in that. And as Nick said, we look forward to your comments. We're always looking to figure out how to improve the user experience for people, and also comments. I'll also say with the micrograph mode that is coming up online, we're working very closely with the European community. I think that's a big game changer because then the field and the microstructures go hand in hand, and it'll be a seamless cooperation between them. And so there's a lot more kind of coming.
Hazel, that Google Doc I think still needs permission.
Yeah. Okay, I'm going to stop talking. If someone could take over that aspect, and I will move on to that.
Well, I just want to jump in and say I really appreciate everybody coming in. Hopefully you got something out of it, and we got a lot of good data already coming in, so that's great. There was one question about when Strabo 2 was coming out. We're starting to field test it next week, and we're going to be out in the field working with it for a couple weeks. Hopefully we'll have a lot of more hardened tests done by then. We're just a new version of Strabo 2 was put up this morning with the last little bit of functionality for the field, kind of the minimal functionality. We'll see how it all works. I guess at this point, that's about all we have prepared. Do any of the other organizers want to add anything, or does anybody want to throw in a comment or question? We can stay on for a little bit.
Looks like that the Google Docs.
It looks like this new link might still require permission, but I'm going to send out an email to everyone, kind of wrapping up the workshop in a few hours here, and I'll include a new link in that email in case this one still isn't working.
And Alex, do you have the link to collect the forms for people who want to partake in the upload a project for money part?
I do not, but we can talk, and I'll send that out in the email as well.
Okay, great, thanks.
Yep, sorry about this, folks. This is my first Google poll, and might be my last for a while. We'll figure out how to get it done. I thought we had given it a test drive, but apparently not.
Oh, I was away for a second. Did I miss a Google poll disaster?
Yeah, exactly.
Bummer.
I'll give one more teaser. The petrology workshop is in a week and a half from now, and at some point during that, there'll be a live demo from the field of Strabo 2, right, Basil?
That's the plan. And also that one's going to be a little bit more workshoppy. There'll be more discussion about, you know, is this the right vocabulary and so forth. So a lot of it will be very similar, however, but we do have these nice little tidbits like field demos. So, all right. Thank you, everybody.
Thanks.